Good afternoon, and welcome to the 2021 Romanowski Lecture of the Royal Society of Canada. Bonjour et bienvenue à la conférence Romanowski. The Miroslav Romanowski Medal is awarded every year for scientific work relating to environmental problems. The medal was established in 1994 at the generous bequest of the estate of internationally renowned metrologist Miroslav Romanowski. An annual lecture series for the award recipient is held by the medal winner. Today's lecture will be given by the 2020 winner of the Romanowski Medal, Professor Ajay Dalai. Professeur Ajay Dalai est titulaire de la chaire de recherche du Canada en bioénergie et en traitement chimique respectueux de l'environnement. Il est également expert international de premier plan en matière d'énergie renouvelable, de traitement du pétrole et du gaz et d'ingénierie des réactions catalytiques. Ces recherches novatrices ont donné lieu à de nombreux brevets pour les procédés et les catalyseurs qu'il a mis au point et ont un impact important sur l'industrie canadienne du pétrole et de la bioénergie. Professor Ajay Dalai is Canada Research Chair in Bioenergy and Environmentally Friendly Chemical Processing and a leading international expert on renewable energy, oil, and gas processing and catalytic reaction engineering. His innovative research has resulted in numerous patents for processes and catalysts he has developed and has significant impact on the Canadian petroleum and bioenergy industry. Professor Dalai is a fellow of the FRSC. Please submit questions throughout the session. Q&A will be held at the end of the lecture. Ladies and gentlemen, Mesdames et Messieurs, please welcome Professor Ajay Dalai.
Good morning, good afternoon. Thank you all for joining this particular lecture, the FRSC Romanowski Environmental Hour lecture. Just wanted to thank the committee that nominated me and then awarded me this particular prestigious medal. So today I'll be talking about the clean, sustainable energy production for pollution abatement using bioprocessing technologies. So I'll give just introduce the topic to you and talk about the biomass, a possible solution for world energy crisis, and then talk about the biomass conversion technologies for clean, sustainable energy production. Then talk a little bit about the supercritical water technologies, and then bring your attention to the work that we have been doing for a while, and then summarize and conclude my presentation, followed by some acknowledgement. So when you look at the carbon dioxide concentration in the environment from the ice age until now, for about from 800,000 to about 300,000 years, we had the CO2 concentration varied in the atmosphere from 200 to 250 parts per million. And we can see that over 100 years ago, it would jump to over 300 ppm. Now it has gone over to 400 parts per million. And in this, and if you look at a little bit more closely about the CO2 concentration and temperature rise, we see that over last 50, 60 years, there has been a drastic increase in CO2 concentration in the environment, and that translates to rise in temperature as well. And what happens in the planet is in the northern hemisphere, when you have summer months, we have a lot more forest in northern hemisphere. So due to photosynthesis, a lot of this carbon dioxide is sequestered by plants, and then the overall CO2 concentration goes down in the southern in the summer months when we have in northern hemisphere, and in winter months we don't have a lot of photosynthesis going on, not much CO2 sequestration. Therefore, the CO2 concentration goes up. But nonetheless, there has been a rise in CO2 concentration over time, and also there is an increase in temperature as well. And so this is because of the industrialization, more energy consumption around the planet over the last 56 years or so. And if you look at the total and per capita CO2 emission on the graph in the left, we find that the total emission varies from country to country. For example, China and USA emit roughly 9 billion and 5 billion metric tons of CO2 per year, and followed by India, Russia, Japan, etc. But when you look at the per capita emission, we find that United States, Canada, Saudi Arabia, and Australia, they're on the top of the list. And we emit a lot more CO2 per capita than many other countries on this planet. And why that happens? Because of the more usage of the petroleum, natural gas, and coal, which are non-renewable energy sources. Their usage is going up, and that translates to more CO2 emission. And if you look at the global emission in the pie chart in the right, China emits roughly 28% of the CO2, and United States about 15%, India about 7%, and you can see the rest of the world outside this pie chart is about 21%. So this leads to increase in global warming, and also leads to rapid depletion of fossil fuel. So there is a sustainable approach, that is use of renewable resources, bio-based fuels, and also we can look at reducing energy consumption. And when you look at the global fossil fuel consumption, it's quite uneven in the planet. For example, China, United States, Russia, Canada, and few other countries, they basically use a lot more fossil fuel total than as compared to many other countries on this planet. And the fossil fuel consumption and CO2 emission, they basically go hand in hand. For example, United Arab Emirates, Canada, United States, and Australia, they emit more, they consume more fossil fuel. Therefore, we have per capita more emission of the for CO2 as well. And when you look at the world's population growth and energy consumption, in about 2100, we'll have more than 12 billion people from 7.8 billion at this point. And over the last 20 years or so, we'll have more, about 77% more non-renewable energy consumption, in spite of growth in renewable fuel production and implementation. So when you look at this fossil fuel usage, we find that it is basically a non-uniformly distributed over this planet. There is high emission of oxides of sulfur, nitrogen, and carbon. And it also accelerates the global warming, depleted resources. And you can see that over the last 20 years or so, there has been an increase of 0.5 degrees C of the temperature of the globe. And over all these greenhouse gases, we have about 81% coming from carbon dioxide, 10% coming from methane, and another 9% coming from other sources. And methane, as you know, has a 21 times more greenhouse gas effects as compared to carbon dioxide, and we really be mindful on the CO2 emission, methane emission as well. And if you look at this, this cartoon here, when we emit a lot of pollutants, including carbon dioxide to environment, it not only leads to global warming, it also leads to acid rain, and that causes soil erosion, and that leads to deforestation, and leads to poor air quality. And most importantly, it is hazardous to human and animal health. Now, let me bring your attention to Canada. So when you look at the greenhouse gas emissions in Canada, we have 7 different sectors, as you see in this pie chart. And oil and gas sector and transportation sector emits about 50% of the carbon dioxide that we emit to environment in this country. And transportation industry is the basically largest polluter of air pollution. And in addition to ones coming from the electricity generation facility, heavy industry facility, buildings, agriculture, and other resources. And in Canada, like the planet, we have also roughly 80% of the total CO2 emission of the total emission, and 13% comes from methane as you see in the bottom pie chart. So let's look at Canada's commitment to sustainability. Canada and the Kyoto Protocol, as we know, that we are committed to reduce 6% in greenhouse gas emission by 2012 compared to 1990 level of 461 megawatt. Now we are at 720 megawatt of CO2 greenhouse gas production. And so none of the countries in the planet could really meet the Kyoto Protocol. Then in 2015, we had Paris Agreement. And under this agreement, Canada pledged to reduce its greenhouse gas emission by 30% below 2005 levels by 2030. And developed countries, including Canada, are committed to spending at least $100 billion a year between 2015 and 2025 to help emerging economies deal with the effects of climate change. And none of the developed countries has really spent that kind of money. By 2023. There is a commitment to spend about $100 billion a year by each country for tackling the climate change. And in Canada, the COP26 agreement that we just finished, Canada is committed to a zero emission car accord and to make heavy trucks and buses emission-free in less than 2 decades. And Canada is among 19 countries to eliminate greenhouse gas emissions from international shipping routes. And if you are able to make it zero emission, then it will be less by 25% in greenhouse gas emission as we are today. And how do we now tackle the climate change? We have to really look at reducing the emission of greenhouse gas with alternate renewable energy sources. And biomass can be produced within a relatively short cycle. Biomass utilization as energy source maintains a closed carbon cycle, and plant biomass contains negligible amount of sulfur and nitrogen, and biomass-derived fuels such as bio-oil can prove to be promising substitute for the conventional fuel, fossil fuel-based fuels, especially for the automobiles, heavy trucks, and aviation industry. So if you look at this particular slide, you see if we use the biomass for energy source, we basically sequester carbon dioxide through photosynthesis to grow the plants, and the plants can be transformed to biofuel to fuel the vehicle, and we can burn that fuel to emit the carbon dioxide that is again taken out by the plant. So this particular process is more or less carbon dioxide neutral process. And now let me switch to the biomass, a possible solution for world energy crisis. And if you compare the petroleum derived fuels with first and second generation fuel, we find that petroleum refinery gives diesel, petrol, kerosene, jet fuel, etc. And when we started working on the first generation fuel about 25 years ago, we find that we can also produce biodiesel and corn ethanol, etc. But we had food versus fuel issues, and it was non-sustainable. And for that reason, we jumped to the second generation fuel from lignocellulosic biomass, where you can also produce the biodiesel, ethanol, etc. And we are not competing with the food. And they are both, of course, first generation and second generation fuels are environmentally friendly. So biomass can be a possible solution for world energy crisis because they are renewable, they are clean, they are, lead to very low emission, they are carbon neutral, and they're more or less uniformly distributed over this planet in all the countries, unlike the petroleum sources and non-conventional energy sources. And we are also have to be very mindful for food versus fuel issue. And here we have examples of the agricultural residue, sewage residue, municipal solid waste, animal residue, industrial residues, and forest residues. And in the world, we roughly produce about 220 billion tons of biomass every year. And we have really opportunity to turn those materials to fuel. And if we don't do that, and we let them rot into in environment, they also produce a lot of methane, which has 21 times more greenhouse gas effects. And we are not doing any good to environment if we don't utilize this resource every year as we produce. So now let me bring your attention to renewable energy and biofuels. If you look at the graph in the left over last 20 years or so, we have almost more than doubled the renewable energy generation. What I mean is the hydropower, wind, solar, biomass, etc. And when you look at the biofuel production, and we have basically gone from 200 terawatt hour to 1,000 terawatt hour, and that's about 5-fold increase. And we also are basically looking at producing more biofuels from biomass. And this is only about 15% of the total renewable energy. And I believe that this percentage of energy production from biofuel, from biomass, will increase drastically down the road. And let me again bring your attention to Canada. We have about 0.5% of world population living in Canada, but we have more than 9% of world forest. And when you look at the annual available biomass from forestry and agricultural sector, it's about 143 million tons of carbon for a year. That can translate to more than 1,500 terawatt hour of energy. And right now in Canada, we are producing roughly 16 terawatt hour of energy. So we have opportunities to go more than 25-fold increase in biofuel energy production with the amount of biomass available in this country, in our country. And the residual and waste biomass, you can see that about 60 million tons that can translate to more than 400 terawatt hour. And that is also quite substantial. And if you look at the renewable fuel standard and low carbon fuel standard in Canada, the federal government has mandated 5% ethanol and 2% biodiesel. In Canada, we use roughly 25 billion liters of diesel fuel every year. And at 2%, we need about 500 million liters of biodiesel. And there are 21 companies in this country, in our country, which produce more than 450 million liters of biodiesel. And when you look at all these different provinces, they are more aggressive than the federal mandate. For example, in Saskatchewan, we have a mandate of ethanol for 7.5% as compared to 5% by federal government. And if you look at Ontario, the renewable fuel in diesel varies from up to 4% as compared to 2% mandate by the federal government. And these are all really, really good signs. And what is the trend in growth of biofuel sector? We are more targeting the liquid fuel. Why? Because they have more energy density. They can serve the fuel for jet engines. And by the by, the aviation industry emits about 2% carbon dioxide of total emission in the world. So if you put more biofuels in the jet engine, then we'll be that more sustainable in and reduce the CO2 emission. And also looking at the production of this liquid fuel more from lignocellulosic biomass than the food sources. So what is the lignocellulosic biomass? It basically contains cellulose, hemicellulose, lignin, extractive, and some of these are given in this particular slide, and they are present in grass, wood, agricultural residue, etc. And in case of lignocellulosic biomass, as I mentioned, we have about 35 to 50% cellulose, 20 to 40% hemicellulose, and 10 to 25% lignin. And by using this biomass, we are basically economically we can benefit, no net CO2 increase on combustion, and they're abundantly available. And the drawbacks are there. They're seasonally available, needs pre-treatment for conversion. And the examples are energy crops, wood, and agro waste, etc. So what is the basically energy crop? It's any plant grown as a low cost, low maintenance harvest used for making biofuels or combusted for its energy content to generate heat or electricity. And they are fast growing, short rotation, and high yield. Will be able to grow in marginal or degraded land. It requires less intensive agricultural practice, and there is no competition with food crops for nutrient or sunlight. And examples are willows and poplar in wood-based energy crop, and elephant, grass, timothy grass, in case of switchgrass in the family of grasses. And just wanted to bring to your attention that with annual availability of energy crop in Canada, up to 17.3 million tons, we have a potential to produce about 4.7 billion liters of ethanol per year from this material. And not only we can use in-house, Canadian mandate can go from 5 to 10% ethanol, and we also will be able to export a lot of these lignocellulosic derived ethanol to other parts of the world and make lots of money as well. Now let me switch the discussion onto biomass conversion technology for clean, sustainable energy production. So there are three different pathways. One is chemical conversion, biochemical conversion, and thermochemical conversion pathways. And part of the chemical conversion pathway, in case of hydrothermal upgrading, biomass is treated with water at a relatively moderate temperature and high pressure up to 20 minutes to remove about 85% of oxygen from the biomass in equal parts of CO2, carbon dioxide, and water. And then we can produce liquid fuel. In case of high pressure liquefaction, we can basically get oil. In case of biochemical conversion pathway, in case of anaerobic digestion, we basically produce the biogas, which is a mixture of methane and CO2, has good heating value. And through fermentation, we can also get ethanol. With acid enzymatic hydrolysis, we convert lignocellulosic biomass to sugars. In case of thermochemical conversion pathway, that is the area that we have been working for more than 20 years. We work mostly in the gasification and pyrolysis. And gasification is basically a decomposition of biomass with controlled amount of oxygen at high temperature to produce syngas, which is a building block for fuels and chemicals. In case of pyrolysis, biomass is decomposed at moderate temperature in the absence of oxygen to produce bio-oil. In case of combustion, as you know, that we supply ample amount of oxygen to produce energy from biomass. And once we, when you look at the biomass and gasify it to different components, we can certainly use the reforming reaction by adding some catalyst and water to produce high quality hydrogen from these intermediate products. And in case of biomass to liquid conversion technology, let's talk about pyrolysis. It's basically a thermochemical decomposition process at high temperature in the absence of oxygen to produce oil, biosolids, and gas. And it's divided into slow, fast, and intermediate processes depending on the residence time of this biomass in the reactor, which can vary from seconds in case of fast pyrolysis and an hour in case of really slow pyrolysis. And in this process, we basically get different amounts of oil and char and gas depending on the temperature and the residence time of the biomass in the reactor. Of course, there are many drawbacks of biomass for energy production. They have a low energy density, they are bulky solid, therefore they are uneconomical for transportation for long distance, they have varying composition, they have different physical and chemical properties, and of course, in many cases, there are a lot of robust technology, mostly in the developing and underdeveloped countries. So like any other industry, biofuel industry depends on the feedstock, on the processability, and also many other factors, including the government incentive and interest from the academia and industrial activities. Now let me switch to the supercritical water gasification and hydrothermal liquefaction challenges and opportunities. If we are not familiar with the supercritical water gasification technology, basically at a critical point, which is about 374 degrees C and 22.1 megapascal, beyond this, the water is called supercritical water. And in this case, the ionic property, density, dielectric constant, viscosity, everything is very, very different than that of water. So what is the advantage of using supercritical water gasification, even if it's a bit energy intensive? And some of this energy can come from biomass itself and also from the solar and nuclear sources. And the advantage are no biomass drying is required because the drying is expensive, and they have a better solvation property, and they basically have negligible or no toxic byproduct, and they produce hydrogen-rich synthesis gas. And if you look at the graph in the right, we can see the pressure versus temperature for water, and we see the supercritical water gasification region and hydrothermal liquefaction region. And the one in the left, we can see the temperature versus treatment time and how hydrothermal gasification leads to production of more gas. Hydrothermal liquefaction is for more liquid, and hydrothermal carbonization is for more biosolid, like coal, like biocoal, and hydrothermal pretreatment is to remove moisture and volatiles from the biomass to increase its heating value and reduce the also transportation cost to some extent. And when you look at the properties of water under different conditions, we vary the temperature and pressure for water from 25 degrees C to 400 degrees C, and atmospheric pressure to 50 megapascal. And we find how the temperature, density, viscosity, dielectric property, ionic property, heat conductivity, and heat capacity changes. And we basically rely on variation of these properties to convert biomass to liquid or gas as needed. So we use basically different kind of reactors. When we started the work about 20 years ago, we looked at basically the different phase behavior in hydrothermal reactor in diamond anvil cell at the Canadian light source. And we have been using the batch reactor and tubular reactor to look at the product yield and conversion of biomass to these different products. And of course, the continuous reactor, fluidized bed, and stir tank reactor can be used when you scale up this process to industrial production. Now let me switch to our own research on clean energy production from biomass. And before 25 years ago, I was trained as a petroleum engineer. When I joined this university in 1996, I was asked to generate research on the clean energy production from biomass, and with the Canada Research Chair position. So I looked into this, and those days, the clean energy production from biomass was not in the radar of province or the government, federal government, and we really have come a long way. At that time, there was no funding available. Now there is plenty of funding available, a lot of passion to contribute to this research. Now also get very high quality students to work with us as well. So though we have listed many in this slide, I'm going to talk about hydrothermal liquefaction and gasification, and also look at producing activated carbon for mercury and carbon dioxide capture. We have been also working on biopellet production to replace the biocoal for energy and electricity production. And biodiesel work we have been doing for over 20 years now, made a lot of progress in that area, and other so on and so forth. So now let me talk about the hydrothermal liquefaction process. So this is basically thermal depolymerization of biomass process at relatively high temperature and pressure, with or without catalyst, to produce bio-oil. And in this process, high moisture and low energy material is converted to low moisture and high energy material. And if you look at this, the schematics here, we'll take the biomass, add water, and pressurize at different temperature, and produce the four different products. One is aqueous product, which has many chemicals. They can be extracted. Bio-oil that can be converted to biodiesel, and solid residue can convert it to high carbon, high quality carbon material. And we also the gases that can be burnt on site to supply the energy that we need for this process. And in this particular example, we are looking at a non-edible, about 15% agricultural material, and adding 85% water. And if it has some inherent water, we just add balanced water to the process and increase the temperature and pressure. And we basically, in a short period of 1 hour, we get 4 different products, about 85% aqueous and 5% bio-oil, and 8% solid residue, and 2% gas phase. I just wanted to bring to your attention that when you started working on petroleum in Alberta, for example, the oil sands has only 10%, 10% bitumen, and it has, with the contribution from the government, about $800,000 in about 1975. Now it has led to billion-dollar industry. So in this particular technology, also when you look at only 15% biomass that we are putting in, we are getting 5% bio-oil, which is about 1/3 of that material goes into the oil, which is a very useful to transform it to transportation fuel. So once you get the bio-crude, we add different solvents to separate the biochar from the bio-crude solvent and water. And by distillation, we can separate the solvent and water and then produce the bio-crude that we need to upgrade. And when we look at this, this is a very, very interesting slide in the sense that the heating value of this crude is about 36 to 40 megajoules per kilogram, as compared to 14 to 18 kilojoules per kilogram for the biomass, and it has a low oxygen content, about 9%, has very negligible gas content, and it's oxidatively stable up to 3 months at room temperature. And all this high calorific value is because of the large amount of aliphatic hydrocarbons present in the bio-oil. And when you look at the boiling point distribution and compare this with the petroleum fraction, we find that the more heavy gas oil and light gas oil materials are present in this, the range of hydrocarbons are present in this bio-oil, and that's really, really good sign. And this is a bit complex, but just wanted to bring it to your attention that many reactions take place in hydrothermal liquefaction process in a short period of 1 hour, when lipids, proteins, sugars, cellulose, hemicellulose, lignin, etc. go through this, this particular process. There are many intermediates, but nonetheless, at the end, we get gaseous product, bio-crude oil, and aqueous product, and biosolid, or the solid residue. And what happens is in this particular work, so we produce basically alkenes, organic acids, oxygenated aromatics, furans, perfurans, etc., from the lipid, lignin, cellulose, hemicellulose that are present in the lignocellulosic biomass. And when you look at the textural properties of the bioresidue that is produced, it's about 8% in the product. So with the different solvents, ethyl acetate, tetrahydrofuran, petroleum ether, we produce a material very high quality biochar, I'll call it bioresidue, with a surface area, high surface area, high pore volume, and good pore size, and that really are very useful for further applications for either adsorption or catalysis. Of course, there are many challenges of using bio-crude as a fuel because they have complex chemical composition, they have multiple phases, they have different polarity, they have high oxygen content, and this high viscosity and density because of the aliphatic hydrocarbons, and then the high acid number because of the presence of carboxylic acid in this material. So we have to overcome these challenges. What we can do is basically blend it with the petroleum feedstock and send it to petroleum refinery for further processing. And when you blend it, it can decrease the viscosity, density, and surface tension. It can increase the calorific value. It can increase the cetane number. And also blending, as I mentioned, can help to feed the mixture to refinery for further processing. For that reason, we looked at a different refinery intermediates and found that the boiling point distribution basically falls in different heavy gas oil and light gas oil ranges of materials, as you see in this slide. And when we summarize it a little bit, look at more closely, we see that the bio distribution with the solid square in this graph matches very closely with the hydrotreated heavy gas oil or hydrotreated cracked product from petroleum sources. And we also looked at blending of the bio-oil with heavy gas oil, and we found that we can go blend up to 10% in 90% heavy gas oil at 120 degrees C in about 12 hours. And we also can blend at different amounts of bio-oil at 120 degrees C at different timings as well. And this is really a good sign that we can create a homogeneous mixture of bio-oil with heavy gas oil and feed into refinery for upgrading. And for that reason, hydrotreating is a catalytic process that is used to remove sulfur, nitrogen, oxygen, aromatics, etc. from petroleum refinery feedstock. And we are very much familiar with this process. We have been working with several petroleum companies, including CCREL, and over 20 years now. And so we basically use this technology to upgrade the bio-crude oil blend at different conditions. And wanted to also share the distillation curve for a hydrotreated blend for the product. And we find that when you use the commercial catalyst, we are able to achieve about 40% biodiesel and 3% biogasoline from this product. And the rest we need to hydrocrack to bring it to smaller molecular weight material in the range of biogasoline and biodiesel. So this particular table shows the results on the hydrodeoxygenation of the bio-oil or 10% bio-oil in heavy gas oil. And the last row that you see that we are using our own patented catalyst to remove about 60% oxygen from this blend. And we are also able to remove about 15% sulfur and 50% sulfur and about 10% nitrogen from the bio-oil as well. And now let me switch to the biomass-based hydrogen as a clean and sustainable energy. As you see this graph, biomass-derived hydrogen basically sustainable, clean as compared to the ones coming from fossil fuel. And in this one, we, as part of this, this activity, we have been using a hydrothermal gasification technology for sewage sludge, municipal solid waste, food waste, animal manure, forestry biomass, agricultural biomass, mixed plastics to produce high quality hydrogen through this technology. And what happens is when you put the biomass in a supercritical water gasification reactor, then it basically, in presence of catalyst or without catalyst, we convert that to hydrogen, methane, carbon monoxide, and carbon dioxide. And with the reforming reaction, we can produce high quality hydrogen for different applications. The reactions are very complex, and it's very difficult to be selective to hydrogen production, but nonetheless, with the catalysts such as nickel-based catalysts, we can mobilize the process to produce more hydrogen as compared to other products. So in this particular work, we basically have used a Timothy grass, which is energy crop. Canada has more than 17 million tons of the energy crop. And we basically wanted to tap that to produce high quality hydrogen. So these are some of the variables and some of the catalysts that we used in this particular process. So this graph shows that we are able to, when you use the carbonate and hydroxides, basically alkali materials with potassium carbonate, we basically produce the potassium acetate, and that helps in water gas reaction to produce more hydrogen. And in case of potassium hydroxide, we are able to produce as well more sodium hydroxide. We are producing more methane. So methane also has a very high calorific value. Hydrogen is a clean gas. It's basically manipulating the process and the loading of these materials to produce high quality gaseous product. And in this slide, we see the potassium hydroxide gives a lot of gas, for example. And if you take 1 kg of the Timothy grass, we can produce about 750 liters of gas. And out of that, more than 200 liters is hydrogen. And we also are able to produce a low heating value gas by producing more methane, for example. And again, the reaction is very complex. We have a cellulose molecule here that goes through homogeneous and heterogeneous processes to convert this material through different intermediates to high quality gas. And we also produce this biochar. As you see here, we reduce the moisture in the Timothy grass from 6% to 2% in biochar produced at 650 degrees Celsius, and fixed carbon is increased about 150%, and volatile matter is decreased, and fixed carbon is increased, and so on, and the oxygen content is also a decrease in biochar. So this is a very high quality char for other applications. We also used Raman spectroscopy for biochar to look at the aromatic nature of the material, and this D by G ratio, which gives the aromaticity, which increased by increasing the temperature for hydrothermal gasification, and and makes it more aromatics. And also we have other different functional groups, as you see, are present in this biochar, which are very much required for many further applications. And scanning electron microscopy shows that we increase the temperature for hydrothermal gasification to say 650, 550 degrees C. It gives more cracked surface, as you see in this. And about the biochar, when you increase the temperature from 300 to 700, we have a more aromatic carbon, more ash, more pH, more surface area, more pore volume. But when we goes to lower temperature, you get more yield, more volatiles, more conductivity, more cation exchange capacity. So depending on the application, we can also produce quality biochar from this lignocellulosic biomass, and some of the applications are given in the right. So we have been more focusing on the catalyst, adsorbent, water treatment for this kind of material. And to produce high quality activated carbon from biomass, so it has to basically go through a biochar, and then depends on the activating agent and condition to produce highly porous physical and chemical structure for this material. And for example, we can sell say 1 pound of activated carbon for $2 per pound, as compared to $40 a ton of lignocellulosic biomass, for example. And in this slide, I just wanted to bring your attention to the work that we did for removing mercury from the coal-fired power plant with the SAS power. And Canada emits roughly 2,500 kilograms of mercury that falls in the land and water and pollutes. And also we get that as a food source through food, fish, and agricultural crops. So we wanted to remove this mercury with the activated carbon, and we find that at different temperature, it behaves differently, the mercury removal efficiency. And we also added halogens, and we find that when you use 1% potassium iodide onto the activated carbon, we can remove 100% mercury from the stack. And in industry, we applied this for about 10 years. SAS Power has spent $30 million and injects the activated carbon aerosols at about 135 degrees C. And with the commercial material, they can remove about apply 1 pound per million cubic feet of the flue gas to remove 60% mercury. But with our material, we can, with 1 pound of material injected into the flue gas at 135 degrees C, when it's cooled down to 135 degrees C from maybe 1200 degrees C, then it can remove about 95% of mercury at the source. And we also looked at using this material for carbon dioxide capture from the environment. And we found that the hydroxyl and carbonyl groups are very much useful. And we did this surface functional measurements with the near-edge X-ray observed on fine structure at the Canadian light source located on our campus. And we find that the fast pyrolysis process produces better material. I'm sorry, slow pyrolysis process produces better material. And in the slow pyrolysis process, we look at the sawdust and flaxseed, flax straw, poultry litter, wheat straw, and willow ring. And we applied this different material to produce high quality activated carbon. And we find that with the sawdust, we are not only able to increase the surface area to more than 1,200 square meter per gram, but we are able to remove about 78 grams of carbon dioxide for each kilogram of the material applied for the adsorption process. So with that, let me please summarize and conclude my presentation. And we find that though 220 billion metric tons of biomass is available worldwide every year, the development and utilization of biomass conversion technology for clean energy production has not yet been sustainable to meet Paris Accord. Bio-crude oil obtained from HDL technology has a high gross calorific value, low ash content, low amount of oxygen, low moisture content, high oxidative stability, and also gives a more percentage of the biodiesel range hydrocarbons. And with the suitable blending and commercial catalyst, bio-oil is suitable for transportation fuel production. And we also have produced very high quality bioresidue for different applications. And our patented catalyst reduced 60% oxygen, 11% nitrogen, 50% sulfur in bio-crude oil blend. And this bio-crude oil produced from the hydrothermal liquefaction process has a potential to complement conventional fuels through co-refining with refinery intermediates. And also the process parameters such as temperature, reaction time, catalysts are critical for high biomass-derived hydrogen yield and total gas yield with greater low heating value gas via supercritical water gasification technology. We have also showed that we can use that for mercury capture and also CO2 capture. So this is a very, very useful for application for environmental pollution control. So what is the take-home message? That bioresearch is a research pool for sustainable clean energy and biocarbon production for economic and environmental benefits. And they are more or less uniformly distributed over this planet. The investment on bioenergy production is increasing day by day. Appropriate bioprocessing technology should be applied for clean, sustainable energy production and emission control materials, depending on the availability and nature of biomass and product demand to meet Paris Accord and now COP26 agreement. So these are some of the references. So we have been working with many companies to materialize for this or to implement this sustainable clean energy from biomass and also biomaterials for pollution control. Just want to acknowledge my supervisors from Master's, PhD, and PDF in this particular slide, and also collaborators from Canada and all over the world. And again, my research team on the site who have been contributing to the work for over last little while. And again, thank you all for your attention. So I may have gone a little bit over time, but we still have another 10 minutes or so for question and answer. So I'll be very happy to discuss if there is any burning questions in this area. Thank you so much again for your attention. So I'll stop at this point. Thank you.